Hello. In this short video, I'm going to explain some of the fundamental physics behind the greenhouse effect. Now, I should say that this is a slightly technical description that does require some understanding of physics. The fundamental control of our climate is set by the requirement that energy in from the sun about equal the energy that the Earth radiates back to space in the infrared. Now, we know what the energy in per unit time per area from the sun is, and it's about 240 watts per square meter. And again, that's an average over the whole globe and over the day. And what this means is that the energy out has to also equal about 240 watts per square meter. If it's out of balance, then the planet's temperature will adjust so it is again in balance. In fact, if you ask the question, why is the temperature of the climate what it is? That's the temperature it's required to balance the energy in and the energy out for the planet. We can also write energy out as sigma t to the fourth. That's just the temperature radiated by a black body. So that should be familiar to anyone who's taken physics. And so if we say sigma t to the fourth is equal to 240 watts per square meter, we can solve for temperature. And when we do that, we get a temperature of about 255 Kelvin. So this is the effective radiating temperature of the planet. And for those of you that don't think in terms of Kelvin, that's actually about minus 18 degrees Celsius. So let's look at the physics of the problem a little bit more closely. What I show here is a plot of the temperature of the atmosphere as a function of altitude. So the y-axis is altitude running from the surface at 1,000 millibars to the tropopause at about 100 millibars. This is about 15 kilometers altitude. And the x-axis is temperature in Kelvin. And if you remember, we said on the last slide that the effective radiating temperature of the Earth is about 255 Kelvin. And so what that means is that the infrared radiation escaping to space is coming from about 500 millibars, or about 5 kilometers up in the atmosphere. And that's where the temperature is 255 Kelvin. And so that's where the infrared radiation escaping to space is coming from. Infrared radiation emitted by the surface is generally absorbed in the atmosphere. It does not escape to space. Okay, let's imagine that we instantaneously double carbon dioxide. Now, what that means is that we've made the atmosphere a little bit more opaque to infrared radiation. So now, photons emitted from this level of the atmosphere are no longer going to escape to space. They're going to be absorbed. Instead, the new emission level to the atmosphere is higher because you have to go above more carbon dioxide before you can escape to space. And the important thing here, the key, is that this new higher emission level is colder than the old emission level because the atmosphere cools with altitude. So that's the key, because remember, the energy out is equal to sigma t to the fourth. So now we're emitting from a higher altitude whose temperature is lower. And because we're emitting from a colder temperature, we're emitting less energy. And if we double carbon dioxide, we reduce the energy emitted by about 4 watts per square meter. So now energy in hasn't changed. It's still 240 watts per square meter, but energy out is reduced by about 4 watts. And that means the planet has to warm in response. So let's look a little bit at what this looks like. So we show here the same plot I showed before, where we have the old emission level, and then this is the new emission level after we've doubled carbon dioxide, and it's colder. But what's going to happen is the climate is going to warm, and it's going to warm until the new emission level is 255 Kelvin. Because remember, the emission level has to be 255 Kelvin in order for energy in and energy out to balance. That's the fundamental energy constraint for the planet. And that leads to an increase in the temperature of the surface. To illustrate some of the subtleties of the greenhouse effect, let's consider a hypothetical example of an isothermal atmosphere, meaning an atmosphere where the temperature, this red line right here, does not change with altitude. And let's say it's 255 K everywhere. Now, the emissions are coming from some altitude in the atmosphere. And when you double carbon dioxide, you push that emission level up because you're making the atmosphere more opaque in the infrared. But the key thing is the emission, no matter what altitude it's coming from, is always at 255 Kelvin. So it's always satisfying energy balance. It's always balancing the energy in. And so no matter how much carbon dioxide you add, you don't have to alter the surface temperature of the planet. So there's no greenhouse effect for an isothermal atmosphere. As a final example, let's consider an atmosphere whose temperature increases with altitude. Now, imagine that the emission is again coming from 255 K level of the atmosphere. Now, let's imagine again that we've instantaneously doubled carbon dioxide. What happens? Well, we push the emissions to a higher altitude because we're increasing the infrared opacity of the atmosphere. But of course, it's warmer at this new level. And that means that sigma T to the fourth, or the amount of infrared radiation that's escaping to space, is actually now greater than the amount of energy that's coming into the planet. So in this case, in response, the atmosphere will cool off until the emission level is again 255 Kelvin. And that's going to lead to cooling of the surface. So for a planet where the temperature increases with altitude, you actually have an anti-greenhouse effect, where the addition of infrared absorber cools the surface. I hope this short video has helped you understand the physics of the greenhouse effect. Thanks for watching.